Hi everyone, if you're new here, my name is Ryan and today I'd like to solve this FE exam fluid mechanics problem with you guys. You can try this problem for yourself for free interactively using the first link in the description below. It'll take you to a screen just like this where you have access to my free FE exam problems. You can click on the flag this question in the upper left. You can cycle through some of the problems that we've done in our FE exam playlist, which all have video solutions. You can try the problems and it'll give you instant feedback. You can view the explanations. It'll link back to that video solution, similar to a problem like this. And additionally, you can kind of see a written out solution with explicit references to the manual and what the correct choice is, which will allow you to move on to the next question. It'll be a good refresher for you to just go ahead and try those problems, and it's free, so you really have nothing to lose. So I recommend you go ahead and try those problems out. Let's get into this solution. It says the figure above shows water flowing vertically upward through a tapered pipe. The diameter at the lower section of the pipe is 50% larger compared to that upper section. A fluid with a specific gravity of 2, along with water, are used in a manometer connected to the two pipe sections. We're looking for the volumetric flow rate in the pipe. Let's transfer this to a clean sheet of paper here. And let's note down some of our givens. Firstly, it says that the water is flowing vertically upward through a tapered pipe. And additionally, what we have is that the lower section of the pipe is 50% larger. That means that if the upper section of the pipe is D, the bottom section of the pipe would be 1.5 times D, or 50% larger. Additionally, it mentions like some stuff about specific gravity here. If we quickly think about what a specific gravity is, a specific gravity represents a ratio of two densities, a density of some substance related to water. Additionally, it could represent the product of density times gravity in relation to water's density times gravity. Density times gravity is the specific weight. So it represents a ratio of densities or a ratio of specific weights. And that's called the specific gravity. And it's mentioned because this fluid here in this manometer has a specific gravity of 2. So we're going to be needing to use that. It's asking in this problem for the volumetric flow rate, Q, like it's mentioned in the manual. And Q is just the product of the area times the speed, where A is the cross-sectional area and V is the speed at that section of the pipe. Now that we've compiled all the given informations, we can think about what formula we would use to solve a problem like this. We're looking for a flow rate, and you can see from this formula here, flow rates are related to speeds. We're given some information about pressures indirectly because we have these manometers here. These manometers represent static fluid, and as we increase depth into a static fluid, what we have is an increase in pressure. That increase in pressure is just gamma, the specific weight, multiplied by the height that we kind of descended into the fluid. So we know some things about pressure, and we're essentially looking for some things about speed. And there's a relationship between pressures and speed, and that is in the Bernoulli's equation. There's also mention of it in the energy equation. Now, when do we know to use Bernoulli's or the energy equation is if we're given some information about losses, or we have a pump or a turbine inside of our problem, we'd use the energy equation. We don't have any of those things here, so we're going to use Bernoulli's equation. Now, if you go here in the reference manual, this is on page 181 of the reference manual, you can see some information about continuity or the conservation of mass. That's going to be important for us because we have a single flow and we kind of have a constriction. But we know that the mass flow rate, or in this case, since we have an incompressible fluid, the density is the same at point 1 and point 2. What we know is that the flow rate has to be the same in the pipe. It's only one flow. So that's going to be important for us. Additionally, we have some information on Bernoulli's equation. And I like this kind of upper form of Bernoulli's equation, which is head form. The head form only has terms written in with units of meters or combinations of terms. So it's pretty simple in terms of what kind of units you get out of it. That's why I like it. And there's another form shown below. We're going to be working with the head form here. If we go ahead and write down Bernoulli's equation, One of the first things that we're going to have to do in Bernoulli's equation is identify 2 points of interest. Now, where are we going to place our points of interest? The first points that pop out to me are the ones that are connected to the manometers. I would label this point as 2 and this point as 1. And I labeled it in this order because the flow is flowing upward from point 1 to point 2. I picked these 2 points because using the idea of manometry, we can easily find pressures at these points. Points at the same depth in the same fluid have the same pressure. So that's why I chose these points, because they're connected to those manometers that we could find the pressure of. We understand what our point 1 and point 2 is. Now, if we're able to isolate the speed, we can algebraically manipulate it to bring into the problem what we're looking for, which is the flow rate in the pipe. So let's go ahead and do that. The first thing that we're going to do is, again, isolate those speed terms. We have a difference of speeds on the left-hand side, and essentially we have some other terms on the right-hand side. We moved over that 2g term, and we have a difference of pressures on the left-hand side. P1 minus P2 over gamma, plus the difference between Z1 and Z2. And this would be what we have on the right-hand side. Now we have a difference of 2 speed terms. If I multiply this left-hand side term by A2 over A2 squared, and this term by A1 over A1 squared, what I end up getting is I'm able to see that the flow rate comes into the problem. Like for instance, for this term, I have an A2 times a V2 squared. That's just a Q value, or volumetric flow rate squared. And if I kind of extract that out, what I have is a 1 over A2 squared term here and a 1 over A1 squared term here. I'm going to go ahead and set that equal to the right-hand side term. Now that I have that right-hand side term, I can move over these kind of set of areas here. And what I'm left with is just that Q term. And it's that term squared. So I can take the square root later, but let's try to find some of these terms. We mentioned some stuff about the manometers and how they could be used to find the pressure. What I know is that the pressure of 1 is given by rho GH, where my density, I have 2 different fluids here, right? If I start at this upper surface, which has a gauge pressure of 0, I descend inside of the fluid until I reach this second point where the fluid is going to change. The pressure at that point is equal to the density of that fluid. It's twice as dense as water multiplied by the depth that we went into that fluid. So the pressure right there is 4 gamma. I'm going to descend by 3 more gamma to end up at this point, which is equal to the pressure at point 1 since they're at the same elevation. That's equal to 4 plus 3 is 7 gamma. And what about the pressure at point 2? The pressure at point 2 is just going to be 2 gamma. We're just looking at water there. Additionally, we did have some elevation terms here. The difference between Z1 and Z2. If we make our datum here, that means that the elevation at point 1 is just going to be 0. The elevation at point 2 is 3 meters higher. So if I go ahead and make some of those substitutions here, what I get is that the Q squared term is 2G. Remember that P1 term was equal to 7 gamma. The P2 term was equal to 2 gamma. And we have a gamma in the denominator here, which cancels out. We'd end up with just a 5 here. And then subtract off the elevation difference. Remember that was 3 meters. And it's subtract because this is this minus sign right here. We have a 5 minus 3 term. That ends up being a 2. And then what I like to do for the denominator is I like to write it in terms of non-dimensional kind of ratios. So if we factor out a 1 over a2 term in the denominator, what I get is a 1 minus an a2 over a1 squared term right here. What is a2 over a1 squared? Remember that a2 was just pi d squared over 4. And A1, it had a 50% larger diameter. So it would kind of be like pi times 1.5d squared over 4. Some of these pi's and 4's cancel out. So essentially, a ratio of areas, A2 to A1, is equal to a ratio of diameters, which both cancel out, and I get a 1 over 1.5 squared. Now that's a ratio of areas. I'm going to again square it when I stick it back in there, because that just represents the single ratio of areas, but I want that term squared. So I have a 1 minus 1 over 1.5, essentially raised to the fourth power inside, a 1 over a2 term squared. Remember, a2 is just pi d squared over 4. If I take its reciprocal, I'll get 4 over pi d2 squared, where d2 or d, that was just equal to 45 centimeters. Remember, I'm going to square this whole term. So I have that in the denominator as well as the numerator. That's this 2 here times 2g. I get 4g in the numerator. Okay, so now if we go ahead and plug in and compute some of these values, we know that g was just equal to 9.81. So I'll plug in, take the square root, and let's also make sure we check out some of these units, right? What are the units of the numerator here? The numerator just has units of meters. That's from this. The 5 minus 3 was just a meter term. What about the gravity? That's measured in meter per second squared. So the numerator has units of meter squared per second squared. The denominator has units of 1 over centimeter to the fourth. Now, what I recall from previous kind of looking at the question was that it was measured in liters per second was those final answers. I know that there's 1,000 cubic centimeters in a liter. Now what I can do here is I'm going to convert everything to centimeters since there's a relationship between centimeters and liters. And in a meter, there is 100 centimeters. I have to square this here. So that all my units work out, I end up with a centimeter to the 6, 10 to the 4th, centimeter to the 6 over second squared. We're going to go ahead and plug all of that in. So our Q term is just equal to 4 times 9.81 multiplied by 10 to the 4th. We're going to divide that by 4 over 45 squared pi. We're going to square this entire thing and multiply by 1 minus 1 over 1.5 raised to the 4th. What I end up getting here is that's measured in cubic centimeters per second. Remember, I went ahead and took that square root as well. And we know that there is 1,000 cubic centimeters contained in a liter. So if we divide that answer by 1,000, what we end up getting is Q is equal to around 11-12 liters per second. So that's what Q is equal to. Let's go ahead and check that solution. It's pretty close to this answer here. Now, if we quickly review this solution, we have the idea of specific gravity. That was the ratio of two specific weights, or the ratio of densities, which was mentioned in this problem. It was relevant because we had this kind of heavier fluid in the manometer here, and that was taken into account when we computed P1. We also had, the continuity equation as well as Bernoulli's equation. And what we ended up doing was, using some algebra in order to isolate that Q equation. And once we had that Q, we essentially just plugged in and isolated for that Q, making sure to work out the units and then computing it in liters per second. At the end, we ended up getting a Q of around 1100, which corresponded to choice C. Now, if this video was helpful for you, please go ahead and leave a like and subscribe for more content like this. Thanks for watching, and I'll see you in the next video. Goodbye.